Right, so this one you have learned it in the AS. So this is just a quick recap on the Doppler shift. Now, we have a source. Let's just say that this is giving us a frequency of 1 Hertz. So every second, it gives out 1 waves. You stand left, right, it will be the same frequency to you, right? If the source is moving, and if this speed of the source is significant enough, then you will see a change in the frequency. If it's moving towards you, right, then the frequency would be, the wave would be compressed. So the way you think about it is like every second it gives out 1 wave, right? So if the source is moving towards you, then that means each subsequent wave that is produced would be closer to you. So that means, in some sense, the wave is compressed, moving towards you. So if the wave is compressed, then the wavelength will be shorter, and then you'll get a larger frequency, and that is the apparent frequency perceived by you, okay? So there are 2 frequencies, this one actual produced by the source, which is the 1 Hertz, and then the frequency perceived by you because the source is moving towards you. So this is, we say, the observed frequency. Now, same if you were to stand on the left side where the wave is moving away from you, then you will perceive it as a longer wavelength or a smaller frequency here. Okay. Now that in essence is the Doppler shift, right? So you have blue shift and red shift. Blue shift, if it's moving towards you, the frequency increase, that means it will go to the right end of the spectrum. So you have your red, Roy, GB. I forgot to bring my pen today, so you have to be a bit patient with my writing today. Hopefully you'll understand my writing, right? So let's say here we have the spectrum of increasing frequency. So when your frequency increase, then it will shift from the yellow, which is original color of the source, and then it will shift to the blue side. So we call it blue shift. The light will turn bluish only if the speed is significant enough, if the speed is moving fast enough. Okay, and then on the other hand, if it's moving away from you, then you will get a red shift. The light will turn, it will appear reddish to you in your point of view only. Okay, in your point of view. Right. So from here, we will derive an equation. So your equation goes, the change in the wavelength. The change in the wavelength means the difference between the observed wavelength and the real wavelength. The real wavelength is measured in the lab. Okay, so we know the actual wavelength of the light. We've done it in the lab, we measure it all in the lab. And then the apparent wavelength is the wavelength I see from the star. Okay, so how do you take the wavelength from the star is you will use like a diffraction grating or anything that can show the spectrum of the, you can use like a prism, let it refract to show the spectrum, and then you can calculate the wavelength. Okay, so from there we get the change in the wavelength over actual wavelength. Okay, change in wavelength over the actual wavelength. Now this, if you look at this, is just a ratio, right? So it's just a ratio of the change. How many percent of the actual wavelength is this one? They said that, okay, this is equal to the same as the change as in frequency over the actual frequency. And this also can be equate to the relative speed of the 2 objects divided by the speed of the waves. Okay, so this V is relative speed. That means it depends on the 2 objects, the source, and also it depends on the observer. Now, in most cases, we will assume our observer to be stationary. So if our observer is stationary, then the V would just mean the speed of the source, because we are just measuring the stars and the V is the V from the stars, and we are static. We are at the same location in space. Okay, so in most cases, this V would just be the velocity of the galaxy or the stars, and then C will be the speed of the wave, right? So in this part, most calculation is just from this formula. You're going to need this to get, and our aim of calculation is always want to get the V lah. It's like they do all this kind of experiment. They just want to get how fast is the galaxy is moving away from us. Okay, so from the line spectrum, we can get the change, the actual. Those are done in the lab. Let's say like the actual frequency and wavelength of the red, we already know. Then we just get the change in the wavelength and frequency of the red. Then we can know, based on that, how fast is the star moving away from us. Okay, so what the astronomer found was that most stars out there, right, is showing all red shift. Is there blue shift? Yes, there's still blue shift, and later we'll explain why there's still blue shift. Remember, blue shift is moving towards us. So some galaxies are moving towards us, and most of the galaxies is moving away from us. So majority they found is red shift. Now, from here, okay, you have seen this one, the emission spectrum. So this is how they measure it. The light or the radiation coming from the stars, from the hot gases. We know that the star is a black body, right? So it emits all the colors. You get a spectrum. Once the radiation comes out from the center of the star, it will pass through layer of atmosphere of the stars. And then the outermost atmosphere of the star is the coolest one compared to the inner one. Okay, so that means you have cool air, like relatively cooler air at the outer atmosphere. And this outer atmosphere, it will absorb part of the wavelength from this radiation. Okay, so remember when we shine radiation through a cool gas, like a cool hydrogen gas, what will happen is that part of the wavelength will be absorbed. Okay, why we want it to be cool? Because originally it is at the ground state, so that it has the ability to absorb the wavelength. So this is all done automatically, okay? Because the star, the light comes out from the center, straight away it passes through the outer layer of the atmosphere, and then it got some wavelength got absorbed. And then when we pick up the light, all this light coming from the stars, we found that, okay, you have missing lines like this. Based on this, we can already study what is the composition of the star in the atmosphere. Okay, so this device that used to show the spectrum, we call it the spectroscope. So like often you may have heard of the word like spectrometry. This is the process of studying the blue shift and the red shift of the stars. Okay, so this is the spectroscope. It's like it consists of many lenses. So you pick up the light from here, and then you see from one side, and inside there are many lenses that can disperse the light, and you can see what is the absorption lines. Yeah, so there's the resulting spectrum. So first we get the spectrum from the stars, and then based on the spectrum, we compare with the actual spectrum of hydrogen. So we know that this one consists of hydrogen. Then we compare the hydrogen from the sun, the pattern, and we compare the pattern of the hydrogen from the lab. And we found that all the black lines is slightly tilted or shifted to the right. This is towards the red end. So that means it's red shifted. Okay, if it's blue shifted, then this will be towards the violet side, blue shifted. So we found that most stars, they shows the gap skewed to one side, to the right side. It shows that it is moving away from us. Okay, it is moving away from us. And not just one line, it's every single line that is being shifted. And how do we get from the previous one, we said that there's a change in the wavelength, right? So we just take note of what is this wavelength, that's the actual wavelength. And then we compare with the apparent wavelength. From there, we can get the change in the wavelength. Okay, so you get the change in the wavelength over the actual, and then we can find what is the speed of the stars that is moving away from us. This is again relative speed, but we are stationary, so that is the speed of the stars moving away. Okay, so this is one of the evidence that supports the Big Bang theory. Okay, now we got two evidences that supports the Big Bang theory. If they ask in the questions, right here, Big Bang theory. Number one is the Doppler redshift. Okay, so what they discovered is that all objects, not only they are moving away from us, they are also moving away from each other. So it's kind of like expanding. Okay, so that is first evidence that supports the Big Bang theory. And number two is they call the microwave background radiation. What is this? Microwave background radiation. Now, first thing is that the Big Bang theory is not perfect one. It's like over the years, right? They come up with a lot of stories how the universe originated, how it all started. There are many, before the 20th century, right? There are many stories or there are many claims that is purely based on belief. Okay, like they believe this is happening, they believe that one. But then after the 20th century, when science came in, right, they start to do some research and they start to pick up all these pieces of evidence that can support the theory. So until now, right, the Big Bang theory is still not perfect, but it is the theory that can explain most stuff that is happening today. Okay, so because they can explain most stuff that is happening today, so they accept this theory currently at the time, like currently they still it's not perfect the point is. Okay, so and then also we'll look at what is the reason that it is not that perfect. Okay, so two evidences that support it is these two: Doppler redshift and the microwave background radiation. What is microwave background radiation? Like, okay, a short story here. Like, it all started. They said it all started based on the Big Bang theory. It started from a point, like space, started from one tiny point. They call it the singularity. Okay, singularity. And back then, about 13.4, I think around this figure, I forgot already, billion years ago, about 13 billion years ago, they said that, okay, the space all is just one dot. There's nothing, there's empty, right? Around it is just empty. And then comes the Big Bang. And then they said there's a misconception on the Big Bang. The Big Bang is not actually an explosion. They say the Big Bang is just like an expansion of the space, but it's not actually a bang, like an explosion. So after the Big Bang, the universe starts to expand. At the early stage, it's all plasma. What is plasma? It's like hot gases, gases that are very hot and very high temperature, high pressure also. Okay. Then after another about 400,000 years, very long, the universe gradually expands into very big size and then starts to form matter. So it's like you get your first hydrogen atom here. Okay, now back then until now, back then, like after 400,000 years after the bang, if you compare this amount of years compared to 13 billion is like nothing. So during this stage is still about 13 billion years ago, still very, very long time ago. Okay, the temperature of the universe, they said, wow, it's about like 3,000 Kelvin. about this range. Okay, back then all the matter starts to form, and what happened is that all this radiation also starts to be emitted from this matter. Okay, you get all this radiation, the electromagnetic radiations. Now, fast forward to today, right? We know that today our universe is much, much bigger in scale. And until today, right, because the universe is constantly expanding, and then all this radiation that was emitted 13 billion years ago continues to travel in the universe. From 13 billion years ago, continue to travel until today. And then the scientists, the astronomer, they say, okay, if this Big Bang theory was true, then we should be able to detect this type of radiation that was emitted this time ago. Because they are still traveling, and at some point they are going to reach us, and we are able to detect it. That's why they keep searching for distant galaxies. They keep looking backward in time. Okay, you have heard like they came up from the new satellite, the James Webb satellite, all that. Okay, they want to discover further into the universe. They want to look more into the back, into the past. Okay, so they say if this was true, if this story was true, then we should be able to detect all the wave coming from 13 billion years ago. And then because the universe is expanding, right? And then they say all this wave that is coming, right? It will be Doppler shifted, red shifted, so far out that it will stretch into the microwave region. So it's like you have radio wave, microwave, infrared, and then there goes your visible light, Roy G. Biv. Right. Normally we only do like red shift until here only. But then they said because this is so far away, it will continue to stretch until the microwave, this one. Like so far out into the microwave region. That means right now, we will be able to detect all this microwave that came from that long ago. And it wasn't microwave to begin with. It was light, but then that is got stretched out because of the Doppler effect, right? Got stretched out into the microwave region. So they make a hypothesis like this one. But then they start to put satellite outside and they start to detect. And they really found all this microwave background radiation. They found microwave background radiation all around the Earth, in every angle. They are picking up the microwave background radiation. So this is also one evidence that supports the Big Bang theory. Okay, so same as the redshift. The redshift says that we are expanding. The microwave background also says that the universe is expanding. That's why we are detecting this stretch out wave. Yeah. Right, so two theory. Now this is the two supporting one. What is the flaw of the Big Bang theory? It's like they said the Big Bang theory, okay, you cannot create something out of nothing. Okay, so that's one thing that is against the Big Bang theory. The Big Bang theory says that it all started as one point. It's like the space, mass, matter, and time, right? All started from one point. But the law of physics says it cannot happen because you cannot create something from nothing. So there is still some flaw in the theory. Okay? Right. Okay, formula This one in your calculation syllabus. Okay, we're gonna try a few examples. Okay, example 1, 2. A particular spectral line in the spectrum of a star is found to have wavelength 600. Okay, compared to 600 nanometer is measured in the lab. So that means this is the actual. Okay, this is the actual. What is the velocity of the star? Okay, change in wavelength. Actual equals to V over C. 600.8 minus 600 over 600 times 3 times 10 power 8. V. Okay, so you will get 4 times 10 power 5. Okay, how do you know it's moving away or towards? You just compare. If it's larger than the actual, then it is moving away, because this one 600.8 wavelength observed is larger than the 600. So we know this one is redshifted. Okay, so redshift wavelength got larger than the actual. Okay, number 2, the H alpha emission lines in the hydrogen spectrum is 656 nanometer when measured in the lab. So that's the actual wavelength. Star A is observed to have that line at 656, star B is at 655.9, and star C is at 656.4. All right, which star is moving the fastest? All right, we just plot like, that's the actual, 656.0. And then star A is larger than that one, all right? So you'll be on this side. This is star A. Star B, 655.9 on the left side. And then star C is at 656.4. Okay, which star is moving the fastest? So the star that is moving the fastest, if this one is the highest, it should have the greatest difference in the wavelength. Okay, so you just minus with this one to see which one gives you the greatest difference in the wavelength. Okay, so it's 656 minus star 8 fastest. Okay, what is the direction of motion of each star? C and A, larger wavelength, so this will be moving away from us. But B is smaller wavelength, that means it is moving towards us. Star B is moving towards us. Again, you compare the wavelength. If it's smaller, that means it is blue shifted. Right. Another 2 examples. Then we go to the next one. Okay, in terms of frequency. Looks like this question is not complete. The frequency of calcium line in the absorption spectrum is observed to have a frequency of, calculate the speed at which alpha is moving away from us. Okay, I think this question is incomplete. Okay, well, never mind. We'll do example 4. There should be more here. Okay, example 4. Shifted by 0.1 mm less than 21. So the change is 0.1. Change to same unit because we are doing ratio times 10 minus 1. I'm going to do it in cm. 21 cm equals to V over C. Okay. This part of galaxy is moving towards the Earth because it says shifted by 0.1 millimeter less than 21. So your wavelength is less than the actual wavelength. So its blue shift is moving towards. How come it can move towards? Isn't it like all galaxies out there is red shifted because of the expansion of the universe? Now, here's the reason is because some galaxy, they have rotational motion, okay? So it's like you have a star here. It could be star or it could be galaxy. Let's say these two stars, they are orbiting one another. They're orbiting one another, sharing the common center of mass, right? So and in any point in time, right, if I'm observing over here, the galaxy could be moving towards me, okay? Right here, if it has rotational motion, it can be moving towards me, but overall, in the long term, they are moving away. Okay, so you say reason is because due to rotational motion or other motion of the galaxies or the stars. Okay, next one. can see. Okay. Okay, now this one we look at Hubble's law. So this graph, recession velocity, recession means like the speed moving away from us. So it is moving away from us against distance. Now recall back, how do we get distance from our formula? Flux intensity equals to luminosity over 4 pi d squared. Okay, it is from this formula that we get the distance. That means you need to know the luminosity of the planet, and the F is measured from the Earth, true brightness and apparent brightness. Then we can get the distance. So they found a way to measure distance. They do it to every single star that they can find outside and the galaxies they can find outside. And then they plot what is the velocity of every single one. They get this graph. Okay, measure distance of each galaxies using the Doppler shift to find the velocity of each star. They arrive to this graph. It's like what you did in the calculation just now, right? So this graph shows that only up to date. That means it can change, and they see a pattern here is that you can like draw a best fit line. It will be a straight line, and the gradient of the straight line is the Hubble constant. Okay, so the Hubble constant value can change if there are like new discovery that can change the shape of the graph. But up to date, they discovered the Hubble constant to be 2.2 times 10 power of minus 18. Okay, so this constant is given to you, second minus 1, 2.2. It's kind of like the gradient of the graph here. The graph on the right, you can see how far they have discovered up to 100. What unit is this? MPC. This is mega. PC is another unit for distance. It's called parsec. 1 parsec is about like 3.26 light year. Okay, how long is this? PC. 1 parsec is about 3.26 light years away. And this is 100 megaparsec. Right? So it's like up to this point they have discovered. Like measure the distance. And they found this is the shape. And over time, this one develops. Like before this, it was only until like 50. Okay. But then over time, they discover more and more, like they can reach further distances. Then this comes the shape of the graph. And then we can draw like a straight line to get the Hubble constant. So it is an approximate value. It is an estimated value. It is never like a 100% accurate values. Okay, so question will ask you, then you'll need to be able to say, is it just an estimation for the Hubble constant, this one. Okay, it's an estimation up to date. Right, so we can write V equals to Hubble constant, distance D. Okay, so given the Hubble constant and the distance, you can find velocity. And also, if they ask, okay, what is the what causes the Hubble constant to be not that accurate? You can also mention the distance measurement here. Okay, I'll write this down here. The distance, we will write down. Okay, let me get some. Right down here. We write sources of error. Okay, the error in the Hubble constant. Number one is that large uncertainty in the distance calculated. Like galaxies that are very far away, the distance that you calculate, the method that you use is not exactly 100% accurate. So that is an uncertainty in the distance, which makes the Hubble constant also not, is an estimate value. Okay. Number two is that when they measure the distance, right, it's not that accurate because the galaxy also, galaxies may have rotational motion. Number 2. And also galaxies precession, okay, the speed where they are moving away, they may be affected by nearby objects with large masses. Okay, so these are the sources of error in the Hubble constant. So the finding was that the longer, like the further you are away, the faster you are moving away. Like if you compare star over here, closer to us, it is moving at certain speed, and star that is much, much further away, they are moving away faster. Why like that? Huh? Say like different velocity for each stars or each galaxies. The one that are furthest away is actually moving the fastest away from us. This is based on its calculation. The way you think of this is you can think of it like the expansion of the universe, right? It's like a dot on the balloon. Okay, so imagine like you place the dot on the balloon and then you inflate the balloon. What you notice is that, okay, think of the balloon like the fabric of the space. Okay, when you inflate the balloon, the dots are moving away, but they are not exactly moving away, right? They are not moving away. It's because of the fabric is expanding. That causes them appears to be moving away, right? But it's actually the fabric expanding from inside out, right? So galaxies, they said, okay, this galaxy is moving away with a certain speed. It could be the space is expanding that is causing like optical illusion that we think that the galaxy is actually moving, right? So this is one analogy that you can think of for the expansion of the universe. It's like the dot on the expanding bubble. And also notice that if I take two dots that are closer, this one and this one, after inflating, they only increase by 1 cm. Okay, 1 cm become 2 cm. But notice that the dots that are further apart, they increase more in the distance. Okay, so this one tells you that the further away the dot is, right, they will appear moving away faster compared to the dots that are closer together. Okay, so this is like the Hubble's, what is suggesting over here. The further you are away, the faster you are moving away. It's like the dot on the balloon. Two further apart one, they will appear moving further out faster compared to the closer one. Okay, so there's a short one on this one. What else you need to know for the syllabus is, okay, the determination of the age of the universe. Okay, now determination of the age of the universe using the Hubble's law, V equals to H naught D. So using this, right, let's say this is observer and we have galaxy moving away with a certain velocity V, and then the distance away is D. It's like it is that far away from us, moving at a velocity V. Okay, this is the Hubble's law from here. We can calculate what is the V based on the distance. Okay, so the fastest speed attainable is the speed of light, 3 × 10⁸. So if I want to calculate how long ago this separation occurs, that means when the galaxy was here. Then I would take, okay, speed equals the distance over time. Time is distance divided by speed, or the v. That means if I take this d divided by the speed of the galaxy moving, then I can get the time where the separation occurs, like how long ago it occurs. Assuming what? What is the assumption we make here? Assumption is that this is constant v. Right? This is constant v. From here to here, it is moving at constant v. So the time can be get from d over v. Right? So from here, we plug in the values. V equals to hd. Right? So we started here. The v over d equals to h naught. And then this will be 1 over t. H naught. And t is 1 over h naught. All right, the reciprocal of Hubble constant. You plug in the values. What do we find is 10 power of minus 18. What we find is 4.55 into a factor of 17 seconds. But how long is this? It's like you convert, our brain cannot understand this thing in seconds. So let's convert to years divided by 2 hours. 24 hours in a day divided by 365. We will arrive to approximately 14 billion years. Okay, so it was that time where the separation occurred 14 billion years ago. Okay, so this part they will ask you how they used to estimate. Again, this is just estimation, okay, estimation of the age. Okay. Now, example. Okay, recession velocity of galaxy has been determined to be 6.4. Estimate the distance in, okay, this one just straightforward, just plug in the values. V equals to h naught, d equals to V over h naught. 6.4 over 2.2. (24 meter per meter distance). The wavelength of a spectral line in the spectrum of light from a distant galaxy was measured to be this one. Same line measured in the lab has this one. Okay, so this, like, from the first part, you will get the speed of recession. Then you will use the Hubble to get the distance to the galaxies. Speed of recession, change in wavelength, V over C. V divided by 393. The second part. Oh, sorry. This one should be V over H naught. Should get 1.84. And also there's a lot of like predictions, like what will happen after the Big Bang. It's like they said that, okay, after some time, if it's long enough, then the universe will stop expanding. Why? Because right now, what is the force left is only the gravitational force from the galaxies. It's like once the Big Bang happened, right? It sends all the stars, galaxies away, and it continued to expand until now. That's why you get all the redshift. And then after like a few billion years, they said, okay, it is anticipated, or it is predicted that you will start to see blue shift. That means all this planet will start to come back. It will start to contract, like the universe will start to contract. Why the universe start to contract is because the only force left right now is the gravity between the galaxies. So it's like they are pulling apart, they are pulling on each other. Okay, which causes the expansion to slow down. So at one point, the expansion slowed down, and then everything will kind of reverse into the same, like to where it started. Okay, that is like the another theory on the Big Bang. Okay, so comes to question, the last question, this one. Suppose that at some distant time in future, astronomers observed that most galaxies were showing a blue shift in their spectra. Sometime in the future, most astronomers observe a blue shift in the spectra. What could you deduce about the expansion of the universe? Okay, then we say, what's the reason? Here you can say the blue shift shows all galaxies are moving towards each other. Okay, if let's say it comes out, like asks you things like that, but we never know, because this is quite a new chapter also, a new topic. If they said, all right, what happened? Why you see blue shift in the line spectra, in the Doppler? Okay, it could be could be the one that we mentioned just now. The galaxy is having rotational motion, all kinds of motion coming. Or if they said, why the whole universe, what could be the reason that you're receiving blue shift? It could be the universe stop expanding and now is contracting. Okay, because of the gravitational force of everybody pulling on everybody. So eventually the speed will get slowed down, and then reverse. Okay, so we write here, since the only force acting should be the gravitational force or the pull of other galaxies. Okay, guys, we finish and take a break. Then I will give you the exercise. Let's take a 5 minutes and let's go back again.